Good afternoon. I'm Dinesh. I'm an assistant research scientist here at High Performance Research Computing. Today, we will be looking at how to run molecular dynamics simulations using specifically LAMMPS software, which is predominantly used in the community who do computational simulations. So the objective here is to reduce the barrier to use LAMMPS for especially for someone who's new to the software, right? Of course, like you might have different projects and different systems that you're interested in. Uh, but here we will go through from the scratch as much as possible, like to the advanced level, to understand how you could use LAMMPS in different ways, how to prepare files, how to use HPC systems to run a job, how to do some basic post-processing analysis that you get from LAMMPS, and so on and so forth. So by the end of this course, the objective is for you to at least be comfortable with the LAMMPS software so you can think about your project straight away without having any barrier to know how to use this LAMMPS software. And to do that, we will be using the Grace, as James was showing in the morning. Just a little bit of introduction. Grace is a 925 node Intel cluster from Dell with InfiniBand HPR100. And it has a number of CPUs and GPUs as listed here, A100 GPUs, RTX, and T4. And the table below, there are 48 cores per node, and the table below shows how many A100 nodes and RTX 100 6,000 nodes are available within Grace, for example. So how do you compute like on HPRC clusters? Like, have you used HPRC clusters for your research? I missed in the morning when you were asked. No? Okay. So the way you use it is if you're a TAMU on-campus user, you will, like anyone, connect to the system through SSH or through the portal that we have, and you will access the login nodes. Login nodes where you prepare the files like and jobs files and modify it to submit a job, and then it goes into the compute nodes, and where the intensive calculations of whatever the jobs that you want to run happens, where whatever the calculations that you want to run happens. If you're off campus, the process is just the same. It's just that you need to have a VPN connection to connect to the systems here offline. So there are two types of nodes on our clusters. One is login node, which is just to log in, perform basic Linux commands, write job scripts, and send the job scripts to the compute nodes. And compute nodes is where your jobs get executed. The calculation that you want to run happens there, and you get it back, whatever the calculation that you're running for post processing, or whatever the outputs that you get from a specific software that you might be running. Now, first we will briefly look at how to access Grace via the portal. I know James showed it in the morning, but let's go over it. This course is mostly going to be where we will be working together on how to run jobs, simulations using LAMMPS. So first, let's try to connect to the Grace via the portal. So let's go to a new tab, type HPRC, TAMU, and go to that website. And here, let me zoom it a little bit. On the top, you'll have many options. One option that you will see is portal option. And we have different clusters, Grace, Faster, ASS, and Launch. We will be working with the Grace. So click on Grace. It will open a new window. And I'm already logged in, but I think you should also be, since you were working in the morning. So make sure you get to this page. Are you both good? Good. Okay. So we are here. So again, you have multiple options on the top. Let me again zoom it a little bit. Files, jobs, clusters, and so on and so forth. And we want to manage our files. So what we'll do is we'll go to Files tab, and under that you will have two options, Home Directory and Scratch Directory. We'll be working in the Scratch Directory. So click on that. And here I will see many folders I've been working on, but you might either see the ones that you were working in the morning or nothing at all. Okay. So this is where we will basically be working on, okay? Are you all able to get to that Scratch folder? Good, okay. So basically this slides basically outlines that step. And how do you access the terminal from here? If you want to access the terminal, now that we are already in the Scratch folder, in your own Scratch folder, each user has their own Scratch folder. From there, you can click on open in terminal that you can see on the top. And if you click, it will open a new terminal for you, which is where we will execute commands to submit jobs and do some edits to files if necessary, and so on and so forth. Okay, those are the two important things. Access the Grace via the portal, the Scratch folder, and access the terminal. Okay, cool. So everything good so far? Okay. Okay, now that we are in the Scratch folder, we need the training materials that we'll be working on, and we are going to copy it from Scratch training folder. The command to execute on the terminal is what you see here, which is the command copy, and you want to copy a directory called md-lamps from the Scratch training path to your Scratch folder. So it's $Scratch. So you can just copy paste it. Do you have access to the slides? You can get it from HPRC website. Okay. You can just copy paste it and run it on the terminal, this line. I'm also going to do it along with you. Control C. Okay, it takes time too. Grace is a bit slow. If it has loaded for you, you can just execute that command. I do it multiple times, so something clicks and it's, huh? That is what I was doing. I just opened three, something suddenly clicks and I start working on it and close the other two. Has it worked for you guys? Yeah. Okay, you guys got lucky. Okay. So if you have typed that command, just do ls to see if that folder is there in your path. You should see a folder called md-lamps. I mean from here or from where? No. Say it again. The in the portal clusters. Oh, okay. Oh yeah, clusters, right? Yeah. Oh, it worked. I don't know why this doesn't work, but yeah, okay, cool. There it is. Okay. So I'm in my home folder, so I'm going to navigate to the Scratch folder to do that exercise. So I'm here, so we're just going to execute that copy command. So what I'm doing is I'm copying the folder md-lamps from the Scratch training path to my Scratch folder. So if I do it, and I should see md-lamps, basically that folder. Now let's go inside so you change your directory cd and you do lamps, and let's go inside and see what is there. So you should see 4 folders that will be basically 4 labs that we'll be working on one by one. So these are like 4 different steps. Are you able to see these 4 folders? Okay, good. Okay, so far so good. So we have the training material. So now let's try to understand a little bit of what MD is before we start working on LAMMPS and how to run MD using LAMMPS. So what basically happens in molecular dynamics is you give an input initial, you have a system. Those systems have coordinates, X, Y, Z, right? It could also have initial velocities assigned to it, or maybe not, right? So if you have those, you will give that as an input structure file to the software that you're going to use. And what happens in MD is based on your initial positions, you could compute potential energy of the system. Now that potential energy ideally should be in a local minimum or a global minimum. If you look at a potential energy surface, it might not be the case. So it will just compute based on the initial structure, some potential energy. It could be huge. It could be it could indicate that your system is unstable in an unstable structure. But that's what it happens. And the way you compute potential energy is using some force field parameters, right? The force field parameters, there are many force field parameters available for different systems. It could be anything. So think of it as just some numbers based on which you need to compute the potential energy, what functional forms you need to use. Once you have the potential energy, you can compute the forces on atoms. And how do you compute forces? It's just simply taking a derivative of the potential energy, and there is a negative sign in front of it. Any idea why there is a negative sign in front of that expression? So think of what we are trying to do, for example, in gradient descent we are trying to take the system to a global minimum or a local minimum, right? We are trying to push it to a favorable structure. So that's negative sign. It's pushing it to lower values. That's what it tries to do. So once you calculate the forces on atoms, this is where the Newton's equations of motion comes into play, right? If you know the forces on atoms, you can compute the acceleration simply by assuming F equal to ma. And once you know the acceleration, you can again get velocities from acceleration, right? Because velocity and acceleration are related. And you can compute velocity and then update position. So this is one cycle. And this can happen again and again and again until your system converges to a favorable structure, or it equilibrates after a certain period of time. So basically what happens is your potential energy is computed, you compute force, from force you compute acceleration using Newton's equations of motion. From acceleration you get velocities, new velocities, and update the velocity positions based on the velocity. And this cycle keeps continuing on and on until the T max that you're interested in. It could be 10 nanoseconds, it could be 1 microsecond if it's a biological system, and so on and so forth. And once the condition is met, if the T is still less than or equal to the T max of interest to you, the cycle will keep running again and again. You'll compute potential energy and it'll keep doing the same cycle again. That's basically what MD does. And once you reach the target time that you're interested in, it could be 10 nanoseconds or anything, right? Then you get some output values of interest that you will compute something on the fly during the simulation, or you would take the coordinates after the run and you do some post-processing analysis with it to compute whatever you're interested in. So that's the basic idea of MD. Now, what is a force field? You need to compute potential energy, right, at the beginning. So you need some numbers, reliable numbers that will capture the system behavior that is in line with what you would see, for example, in experiments. So force field is basically a mathematical model that describes how atoms interact with each other. Now that mathematical model needs some numbers. Where do they come from? For example, it comes from quantum mechanical calculations, from where you can get some numbers, and there are different force field defined for different classes of systems. Like for proteins, there are established force fields, and for materials, there are different force fields, and so on and so on. So it provides the equations and parameters needed to compute the potential energies and consequently forces. And force fields usually are fitted to material properties around certain conditions. How do people come up with even those numbers, right? So you experimentally, you know that a certain standard systems which will have certain density, it should show certain characteristic behaviors, right? Let's take density for example. So you optimize your force field parameters such that you get the experimental density in simulations. Like that, people optimize it again and again and come up with a certain set of numbers to say, okay, if I simulate it with these numbers, I will see this, I'll get a molecular idea of what the system does and can go with what experimental people do. So some common types of force field that you will see in LAMMPS are, there are Lennard-Jones potentials, EAM for metal simulations, CHARM, AMBER that James talked about, COMPASS, Aribo, and ReaxFF is for doing reaction simulations. So the simulation that we will be doing doesn't involve any reactions where there's bond breaking and things like that. So there are also force fields to do reactions if you're interested in chemical reactions. Okay, now that we know basics of what MD is, what force field, what is a force field, like what is LAMMPS here? What does LAMMPS do? So the word LAMMPS stands for large scale, atomic, molecular, massively parallel simulator. So the first letters of those words constitute that abbreviation LAMMPS. And this is the quote from directly from the manual that you will have. So it says LAMMPS is a, I'm just going to read it. LAMMPS is a classical molecular dynamics code that models ensembles of particles in a liquid, solid, or gaseous state. It can model atomic, polymeric, biological, solid state, metal, ceramics, oxides, granular, coarse grain, or macroscopic systems using a variety of interatomic potential force fields and boundary conditions. It can model 2D or 3D systems with sizes ranging only from a few particles up to billions. So you see the value of this software. There's a reason why people use LAMMPS a lot in the MD, in the computational simulations, the community who does computer simulations. There is also another software, GROMACS, that James was showing in the morning, which is also very, very famous for doing biological, like protein simulations and things like that. But LAMMPS is equally good in terms of the ability, the capabilities that it has. So the biggest advantage is it's an open source MD software. Anyone can download and build it and use it. The advantage is if you want to run, as it says, the definition says few particles up to billions, right? Of course, we are not going to do billions of particles today, but let's say you want to do thousands of particles or 10,000s of particles, right? You can, if you do it one by one, if you, for each atom, if you compute potential energy, force, and this and that, you see how already how difficult it is, right? So LAMMPS can parallelize everything on a large number of CPUs and GPUs to run these simulations. So it's much, it does it in a faster way than if you were, let's say you were able to write a MD code, which it's easy. But if you write it in a serial fashion, it's going to be very, very slow, right? So LAMMPS does it parallelly, that, and it may uses the lot of, like, it can run on number of CPUs and GPUs resources to faster make your simulations faster. And LAMMPS is a well maintained it has a well maintained documentation which gets updated with every release. You have the link on the slide, and it's one of the best manual that you could find to learn LAMMPS on your own. Like, if you go through it, any question that you might have, you will find an answer. If you don't, there is also a LAMMPS mailing list. You just go Google searches. If you ask a question, someone will respond to you, trying to help, like how, like if you're facing an issue with a specific thing that you're dealing with, someone might have already worked on it and they might be able to help with that as well. But the documentation should be the first source for you. And yeah, so that link is present here. So we'll be seeing how we could use LAMMPS for different types of systems. What files do you need? What those files even mean, and things like that. So we have 4 labs. So we'll start with a very simple example of Lennard-Jones system. And we will start with a coarse grain model. Coarse grain model in the sense there is no all atoms, like we will represent, for example, a water molecule as just one bead, right? Just a bead. No all atom representation, no carbon, no hydrogen, no oxygen stuff, just a bead. Like let's try to simulate MD simulations of that. Try to understand what LAMMPS does even. So in order to run a LAMMPS simulation, you need three things. Not always, but mostly you will have three things in different forms. And the first file that you would need is a topology file. It describes the number of atoms. It describes your initial positions, charges, masses, etc. Remember, the starting point of an MD is you need to give some input position, input velocity, right? So you need a topology file describing your system, basically. So that is one. And the second thing that you need is an input file. Now that I have initial positions, you need to define what force fields you want to use, what functional forms you want to use, what simulation conditions you want to simulate it at. Do you want to simulate it at temperature 300 Kelvin? Do you want to simulate at 200 Kelvin? What pressure you want to simulate it at, right? What computations you want to do on the fly. So one good thing with LAMMPS is there are not a lot, not everything, but there are many on the fly calculations that you could do when the simulation is running by itself. So you will basically describe your simulation conditions in the input file. So that's your second file. The third one is the submission script, right? This is where you will describe what resources you want to use, how many cores, how much memory you want for the simulation to run using the LAMMPS software. So three files, right? Now, is that clear so far? Right? Yeah. So we are going to simulate a Lennard-Jones system. Again, as of now, just think of it just as beats, right? Like some particles just going to move around. It comes from the Lennard-Jones called Lennard-Jones functional form that you see here, which is basically, think of it like the mathematical model, right? That I was talking about in terms of force field. And if you look at that functional form, you see three parameters. One is epsilon, and the other one is sigma, and the other one is distance r, right? So let's look at this graph to understand what this is. Like this is the basics. So like if you look at the right hand side curve, y-axis is your potential energy, right? That you need to compute. X-axis is the distance between two atoms, two beats in this case, right? Now, what it does is at large distances, you will have a weak attractive force, but as the particles come closer and closer, it will start to find some attraction between the two, right? And you see the maximum attraction at a certain point, which is like 1.1 sigma, right? That is a standard distance value where you see, and that depth is basically your epsilon. How strong your attractions are going to be at that 1.1 sigma, right? So that depth of that well, that curve that you see there, in this case, it's approximately about like -1, right? So your epsilon in this case would be like that, like 1, basically. That's the depth of the thing. And sigma is basically the diameter of the bead. Let's say you have two beads that you're looking at and they are the same diameter, right? It's simply the average diameter. Let's say you have a particle of diameter, just making up some number, let's say 1 angstrom, right? Your sigma is basically 1 angstrom of those two beads, because that is when they're going to be just touching each other, right? And once they touch each other, there will be a repulsion that you see here, because you don't want things to overlap, right? Once they come and collide, they have to just move apart. Like that's basically what is happening in MD. It just comes together, interacts, move apart, and so on and so forth. So the sigma is basically the average diameter of the two atoms interacting in this case. Epsilon is your well depth. It tells how strong the interactions are between the two beads. And R is basically the distance between the two atoms of interest, right? So that's the simplest functional form that you could use. It's also used widely for like many other, like it's used many systems. This for same functional form will apply. The only thing that will keep changing is the epsilon values, the sigma values, and things like that, depending on the atom types that you're looking at, right? What do you think? Let's say you have two atoms that are interacting with each other, but they're entirely different atoms. What do you think the sigma will be in that case? Let's say you have one small atom and then one something very kind of big. They're not the same diameter. What do you think will be the diameter of between the two when they're interacting? It's just the average diameter. Let's say you have particles A and B, it's just sigma A plus sigma B divided by 2. That's the arithmetic mean. It's as simple as that, right? And in the slide, you will also see some links. Let's just click on one. So this is just one example of how LAMMPS does a really good job in explaining what those commands mean, what functional form it is, the one that you saw on the slides, and it explains how to use it, what you should input, and so on and so forth. So every single command that you will have in LAMMPS, it has a page dedicated to it explaining what it is, right? All it takes is just to go and read it and try to understand what it does. Okay. First, let's try to run the job. So in the time we are discussing the files that are there, this job would have at least been completed. So go into your LJ directory and submit the job. So let's see. My thing is terminated. If it's terminated, you just have to start another session. You're already on. What is there inside? Like what are the okay? Give me a minute. It's just loading for me. See what I am doing. So inside the my dashboard. So inside the LJ, you will have two files, lj.in and job.sh. Just submit the job for now. We'll discuss what these files are, but in the meantime, the job will be running. So the way you submit it is sbatch job.sh. You can look at it on the slide as well, the command to submit the job. It's here, sbatch space job.sh. Okay, I'm here. Is the reservation not on? Why is it saying error? It says requested reservation is invalid. Not sure. That's okay. I mean, we are running very small simulations. All that you have to do is the following, right? Okay, you see, are you here on the dashboard, right? You see three dots. Click edit and remove the line where it says sbatch reservation equal to training and save the file. Go back, submit the job. Good. Should have submitted the job. So if you want to see whether it is running or not, you choose to sq hyphen me. It should tell that it's running for me. It should run for you as well because we're asking very less resources, so it should be fine. Good. You're also attending the course?
Yes.
Okay, so are you able to submit the job?
I'm logging into the portal for some reason it's saying that can't find user my actions.
Oh,
Uh,
do you have a Grace account?
I or I have an ACES account.
No.
Progress. Do you have an upload person? Yes. Okay. So if you go into Grace.
It has finished for me. Is it done for you guys? If you refresh it, you now should see a bunch of files showing up. I will discuss, but I just want to confirm that you see a number of files. Are you guys seeing that? That means it has run at least, right? Something has happened. You have to just refresh it. It's on the top, the option. Can you ask someone to process this application or something or not? Okay, let's try to inspect the files, right? Like let's try to see what we have done, right? So first, the easiest thing is let's look at just the job submission script just to understand what we did. So here we just, let me increase the size. We just gave a job name. And job script has nothing to do with specific to LAMPS or anything, right? We are just requesting some resources in order to run your software. It could be anything, right? In this case, it's LAMPS. So here we are giving a name to the job, which is LJ. So if you go to the terminal and look at the SQ option that you ran, you would have seen that the name was LJ, right? That's the name that's coming from your job submission script. And we are requesting the job to run for 20 minutes. So it's hours, minutes, seconds. I just asked for 20 minutes to run the max. And the partition, like Grace has a lot of partition, the one such as medium partition, it has a time limit of how long you can run. And here I'm requesting medium partition to request some CPU resources. And how many nodes? Just one nodes. And how like an n task per node is 5 MPA tasks. Again, it's parallelizing, right? LAMP. So you're just saying how many tasks per node. How much memory do you need? These are very small simulations. So I'm just requesting like 4 gigs here. And I'm asking the output to be printed in a file called out dot the job ID that the Slurm manager will assign to you. So you will see a file called out dot some random number, right? That's basically your output file. It will also print the error. If there is some error in your input files or something wrong with the simulation, to also print the error in the same file, right? You will be able to see what is going wrong or what is going right in your simulation. And we have LAMPS already built on Grace. So I'm just going to use the one that is already there. You can also download a specific version, install, like build it and use it. But here, just so that everyone can use the same thing. So I'm just loading the one that is already built. So these are some prerequisites to load and build LAMPS. So if you want to understand how to load build like environments and stuff, I think there's a course next week by my colleague Tang Ha next Friday to understand how to load modules and things like that to understand. So that's a dedicated course to learn how it does. Like right now, it's just the 2 lines that we will need to load the LAMPS files. LAMPS, the version that we are going to use. And then finally, we have this line which invokes, which tells basically to read the input file MPI run. How many NP basically takes information of nodes and n tasks per node, and LMP is the executable that we would have built it with. Think of it's LAMPS is written with on C++. So you need as executable, right? LMP is just an executable file. And then in is the keyword for input file, and you will give the input file that you had in that path, lj.in basically. Basically, it's going to read lj.in and knows what simulation you want to run And inside the lj.in, we will define the initial positions and so on and so forth. So that's our job script. Now let's go into lj.in, which is our input file. This is where we define our simulation conditions. It takes a little bit of time to get a hang of what these different commands are, but trust me, if you do it like for a week or so, it's just the same commands in LAMMPS. It's just that easy. Yes. Okay, but I think for our resources it should be fine. But yeah, it's small letter LAMMPS.
Yes.
Okay. Okay, let's go over the commands and see what it means. Again, the point is not for you to memorize or anything. There's a documentation, but just to get a feel of what all we define. So we are basically saying the units is going to be LJ. LJ units are basically nothing but it's like it's unitless, it's dimensionless. There is no angstrom or there is no stuff attached to it. It's just sigma and epsilon, like that we showed on a curve. There is no specific unit assigned to it, like angstrom or nanometer and things like that. And the atom style is full. Like what that basically means is, so LAMMPS has a variety of styles, and one such style is full. So basically you're telling what all you need to record during the simulation. So full basically records your coordinates xyz, which is important. Pretty much every style will do it. And charges it will record, and each atom type will have an atom type. Again, I will show you the data file where those information are, but just those, I'm just putting out the words. Each atom will have a specific atom type. And if you have polymer chains, each chain will have a specific ID, and like it's basically assigning different IDs to it. So basically that full command will just basically print that for you. Okay. And boundary, we are saying PPP. What does that mean? Like it's just periodic boundary conditions in X, Y, and Z directions. That's the P. If you don't want a periodic boundary condition in a specific direction, you don't just say that. There are like, if you don't, I think there is, let's look at what boundary is. Like, okay, let's say you want to learn what a specific command line in LAMMPS is. You just type boundary LAMMPS, right? If whatever that you want to learn, right? Like if you do boundary LAMMPS, the first link it tells, it will give you what that command means. So all that you have to do is just go over it and try to understand. So it says boundary X, Y, Z, and you have multiple options. If you say P, it's periodic. If you say F, it's non-periodic and fixed. S and M are shrink wrapped and stuff like that. Let's not go too much into those advanced things. Again, in 2.5 hours, I'm trying to keep it as minimal as possible, so you at least know like what all the capabilities of LAMMPS are, right? Now, what are boundary conditions? I think James touched a little bit on it. We are simulating things in a specific box, right? Like we are defining a box, and inside that atoms are moving and wiggling here and around, like based on the simulation conditions, temperature, pressure, and so on and so forth. How can I make it equivalent to experiments? Experiments are not done inside a box. Experiments are like, in an infinite medium, right? So if whatever I want to compute from simulations should make some sense that I can work with an external collaborator and try to tell them what it does, right? So periodic boundary condition, simply, if I have to put it in very simple terms, it's just if a atom crosses a boundary of one side, it just comes on the other side. What that does mean, it's not like a magic thing. Think of, you have a central simulation box. When James loaded the system and showed it to you, you see one central simulation box, but there are infinite periodic boxes or mirror images. Think of there is a central box and there are mirror images of those box all around, right? So in essence, when we say periodic boundary conditions, we are actually defining an infinite medium, right? We don't define something within a box, because when you define just within a box, you'll have surface effects and things like that, right? But we want to define an infinite medium. So think of, you have a central box, but there are things that you don't like see, which is like mirror images of those central box. Like I will visualize and show it to you later on, but that's what is happening. You're basically trying to simulate an infinite medium, right? If I have to go like too technical, what is the thermodynamic limit of like how many atoms like you could think of imaginable that you could simulate, but we can't. But what is the thermodynamic limit? We all know that number. It's just Avogadro number that we looked at, right? But we can't go that high, right? But we are trying to define, simulate as infinite as possible, as such an infinite medium. So the things that you could compute correlates with what people would see in experiments and things like that. Okay. So here, the thing, in this first lab, we don't have a data file, or we don't have a data file to start. What is a data file? It's another name for topology file. So we don't have initial positions of and a system to start doing the simulations. So in LAMMPS, what you can do is you can actually create that system yourself. So here, the word lattice, it says I'm just telling the LAMMPS to create a system of face-centered cubic lattice of specific density 0.85, right? So it's just a reduced density. It's number of atoms per volume. So basically, what I'm saying is, okay, I'm giving you that the density is going to be 0.85, and in the next line, I'm going to also define region box block the basically the dimensions on either n 0 to 10, 0 to 10, 0, 10, x, y, z. So if I know the dimensions, if I know the density, you could compute how many atoms you need, right? Because density is number of atoms by volume, right? Now if I know the number of atoms, and all I'm saying next line is I'm saying create box, one box, create atoms, put atoms within that box. All it's just going to do is create a cubic box, put that many, it computes itself for how many number of atoms it has to be there to achieve that density that you're looking for, which is 0.85. Okay. And in the next line, you see mass. We are trying to simulate only a Lennard-Jones particle system, right? All the particles will just have a mass of 1. No units. It's just some number 1. Like it's just Lennard-Jones units that's dimensionless. And here, after defining the system, I'm asking the LAMMPS, okay, now that you have created a topology, write me that data file so I can look at it, which is basically your initial underscore fcc.data. I'm asking it to say write data. Most of the commands are somewhat self-explanatory. It says write data file, or the data file is just another name for topology file. And once it writes it, then it continues to do the simulation with the defined system. So I'm going to define a time step. The standard LJ time step is 0.005. And I'm going to assign some initial velocities. Once I have created atoms with certain initial positions, I'm going to assign some velocities here. So it's velocity all, I'm just asking it to create a velocity at a specific temperature. Again, it's a reduced temperature, so temperature here is 1. Okay, so there's no meaning to it. It's just number 1. We are trying to understand what LAMMPS, what MD simulation is. So it's some temperature 1. And we are giving a random seed, and we are trying to say neglect or make the momentum, angular momentum and linear momentum 0. That's what it basically means. MOMS, ROT S. Basically, what it tells is, okay, you start the simulation, assign velocities, but on a net basis, it should be 0 when you average it out. Some will have like go in the positive direction, some will negative direction. When you cancel it all out, it should be 0. I don't want the entire system to be translating in one direction, right? So you're just saying like, make sure you remove the angular and rotational momentum. So for example, if let's go again, velocity LAMMPS. All that you have to do is just type that command, velocity command. If you go here, it will tell you what each one means. For example, let's say it says, for example, MOM, no or S. It says what you should do. You should either give no or S. Now, if you go down, if you try to find where MOM is, okay, here. Okay, here. The MOM and ROT keywords are used by create if MOM is equal to S, the linear momentum of on created ensemble is zeroed. And if ROT is S, angular momentum is 0. So basically your system doesn't drift in space. Think of it as drifting in space, right? You want to avoid it. You're just saying that that should not be the case. Now you immediately can realize that these kind of lines will be the same for any system when you start simulating. These things don't change. And then there is a pair style. We are saying LJ cut, which is the functional form that I just showed a few slides ago, Lennard-Jones functional form. And basically I'm saying cut the potential at a specific distance, which is 2.5 here. Remember at 2.5, your LJ almost goes to 0. If you look at this curve, right, at a distance of 2.5, they are almost 0. There is no net attraction. So I'm saying compute only until 2.5. Anything above that is just waste of time, right? Because the two atoms are not going to feel anything beyond that distance. So why should I even compute it, right? So just go until 2.5. See, where was I? Oh, here, file emitter. Okay. Now these two lines, neighbor commands, right? I mean, they'll be standard in any simulation that you do. Think of it like this. You have a system of 1,000 particles, let's say, right? You need to compute the potential energy or the interaction between each particle with every other particle. If I have particle 1, I have to compute it with all other 90. If you have 100 atoms, all other 99 atoms. Then 2, all other 99 atoms, and so on and so forth. You see already how intensive it is. It goes as order of n square, right? So what LAMMPS does is they define something called a neighbor list and say, okay, I'll create a neighbor list within this cutoff that we define, like for 2.5. I'll only do computations within that. If the atoms moves outside and some other new atom comes inside, I will I'll rebuild my neighbor list. Until then, I won't worry about anything that's outside that neighbor list. I'll only worry about the things inside. So these command just tells LAMMPS to do that. Even if you don't use those commands, LAMMPS has by default some numbers that will do it. I'm just showing it to you so that you know that how it does to parallelize and build a neighbor list and speed it up. It has nothing to do with the system itself. Okay, from here on, things will become like where it's user choices. Thermostyle, what all you want to print. So thermostyle is a command where it's called custom, and you can still tell what all the stuff that you want to print. Here I'm saying I want to print something called time step, temperature of the system as the simulation evolves. PE stands for potential energy, kinetic energy, total energy, and pressure, and the density. Okay. And how often do I want to print those quantities? So that's what the next line is, thermo 1,000. Basically, I'm saying every 1,000 steps, print me these statistics, right? So I can monitor what happens to those numbers. For a bit, let's forget this thing. Like we'll come back to what RDF is later on, but let me just finish it. Even the MST part, let's leave it. Let's try to go over the rest of the part. So then after the thermo command, I'm saying, okay, here, I want to dump the trajectory to visualize the trajectory, right? I did a simulation, but it would be nice for me to see how the movie of that simulation, right? So there are different file formats. I'm saying dump. Again, dump is a command. If you want to learn, you just say dump LAMMPS. You will read a lot of what are the options are. Basically, in this place, what I'm basically saying is I'm giving a name to that command. It's user choice. I'm saying dump me all the atoms. All here means I'm saying all the atoms. You can also dump only specific atoms, but in this case, we'll just print all. And I'm saying dump me every 1,000 steps and record the trajectories in this file traj.lj.dump. And what I want the software to dump is, I want it to dump the ID of the atoms, the type of the atoms, and the coordinates x, y, z, and the image flags ix, iy, iz. Okay. I'll discuss what image flags are when I show you visually the simulation, but think of it as something to do with periodic boundary conditions for now. And then the next command is I'm simply saying sort it based on ID. I don't want it to be random. Like if you have 100 atoms, I don't want it random. I want it to go from 1, 2, 3, 4, all the way up to 100, just sorting it. And I'm saying run the simulation for 20,000 steps. Okay. So these are something that like user defined. You could run it for longer. You could print certain things. You could dump very frequently or like less frequently than what I'm doing here and things like that. Is that clear? Again, it will be like it's too much to remember, but the more you start looking at this, so first XSL, this lab will be a daunting, but what you will see is second, third, fourth, you will start to see the same commands appearing. So that's when you will see, okay, it just comes with like looking at it often again and again, that it becomes so easy to use LAMMPS. Is everything good so far? Okay. I'm going to discuss what RDF is and then come back to it a little bit. So what radial distribution is? That's one of the very basic computation that people still use, and it's also one of the powerful calculation that people still do with MD simulations. It's simply counting, as it says, it's just a probability of finding an atom at a given separation distance from a reference atom, right? If I have an atom A, right, what is the probability I will find an atom B at this distance, right? It's as simple as that. So basically, you have a system like the schematic shown below. Let's say your reference atom is the red one in between, right? You want to see how the red and blue atoms interact during your simulation, right? If they interact very well, if they have attractive force between them, you will see them always being close together at most of the times during the simulation. If they don't like each other, they are not even going to meet during the simulation, right? So the RDF basically computes as that. It tells us the probability of finding an atom at a given separation distance. It's not literally the probability, it's a normalized probability. What it means that is like you normalize everything in case of uniform probability distribution. Now, imagine a box. There are no interactions at all between anything. Everything is just moving around and they are just all forced together to be inside the box and they have no other choice. What do you think will happen? There are no net interactions. So you won't see any favorable things coming together closer or staying together and stuff, right? It's just random. So you will have a uniformly distributed stuff, right? So that if that's our base case, and you have your simulation done, and if you normalize everything by the uniform distribution at long distance, it should go to 1. Because remember, we are cutting our attractions at 2.5. Anything above that, we are not even bothering, right? So after 2.5, there are no net interactions, or like, the interactions are almost going to 0, then your probability should go to 1, right? So already you know that RDF at long distance should go to 1. And how much it goes higher and short, long, or higher or lower at the short distance tells how attractive the two atoms are, like, basically. Okay, we'll come back to this. So go here. So we want to compute RDFs, right? So these lines basically does it. LAMMPS itself can do RDF computation for you, right? So it says compute RDF. That's the command. And you are giving a name of choice. It's your choice. You can give any name here, G of R. And you're saying, okay, anyway, I have just a system of Lennard-Jones particles. Compute me the RDF of all the atoms, right, in the system. And RDF is the command, like the function name. And you're saying 200 bins. You have to bin the system, right? In each bin, you are going to compute what is the probability of finding that atom B in reference to A in that particular bin. So you have to define the number of bins here, and then you have to average, or like, you have to output RDF or average RDF at certain intervals, right? So fix is the command. Fix is one of the prevalent command that you will see in LAMMPS. So fix and any name of your choice. And I'm saying all, whenever you see all, it's just saying all the atoms in the system. And average /time. And this is the thing that's somewhat tricky to, not tricky, but like it's important to understand this because we will do an exercise later on with this. So you see 3 numbers there, right? And those numbers are n every, n repeat, n frequency. Okay. So let's see what that means. Fix average time. Again, I'm also trying to show how easy it is to find that command. All you have to do is fix average time LAMMPS. The first link will be that command. and it tells you that these three numbers are n every, n repeat, n frequency. Okay. Now let's see what that is. Let's go to an example here. Okay. It's a good example to know. For example, if n every is 2, and if n repeat is 6, and if n frequency is 100, what it will do is at the 100th step, when your simulation reaches the 100th step, it will repeat, it will go back in time 6 times in steps of 2 to average the quantity that you're interested in, right? So at 100 steps, if I have to go 6 times in steps of 2, it's 98, 96, 94, 92, 90, right? So whatever the RDF was in those 6 steps, it will take it and average it. You get a feel for that, right? That's basically what those three numbers are. Now, if I go to the file editor, I'm saying 100, 100, 20,000. What do you think it will do? So we are running the simulation for 20,000 steps. So if I say n every, n repeat, and n frequency is 100, 100 to 20,000, let's first get the 20,000 first, right? 20,000 is where we are going to print that RDF. Basically saying, okay, when the simulation goes to 20,000, print me that output. That's all I say. But when you're there, you're saying repeat 100 times, go back in time 100, like 100 times, and in steps of 100. So can you, based on this information, can you tell me from what step to what step you're averaging our RDF? At 20,000, you have to output your RDF. I'm going back in time 100 steps, 100 times in steps of 100. So between what and what time I'm averaging it out? Any idea? So it's just 100 times 100 by 100. What is it? 10,000. So you're averaging all the computation that has happened between 10,000 steps and 20,000 steps. The reason why I am leaving the first 10,000 steps is I'm assuming it to be equilibration period. System equilibrates. Let it relax a little bit in those conditions. Once it touches 10,000, I'll start accumulating the output that I wanted. Is that clear? Right. Okay. There is this thing called MST. This will be useful when we do lab 2. We'll come back to it again, but assume that we are just computing something. MST is nothing but mean square displacement of atoms. We are seeing how much the atoms move in over time during the simulation, but we will revisit how to compute this because we will compare the results from lab 2 to lab 1 later on. So let's forget. For now, let's just keep it aside. Is that clear? Do you get a feel of what we are doing? We are just defining the simulation conditions here, okay? Okay. Now that you know this, let me go over these files. So the initial underscore fcc.data is the topology file that the LAMMPS created and printed. If you remember, like we said, write data, right? Here, write data. After creating the system, it prints those topology information in that file. So that's basically your initial structure, a face-centered cubic lattice structure. And then your RDF results are inside the 2 files. Now, why 2 files, right? If you go here, I'm computing RDF of the initial structure. Before even running the simulation, I'm computing an RDF of that static structure, right? Which is basically the structure that is stored in initial underscore fcc.data, right? This is before running any simulation. And I'm saying I'm also compute the RDF after running the simulation, which is the second part. It's just the same command. It's just I'm doing it twice. And how do you know that I'm computing the initial structure? As you can see in the first step, I'm saying run 0. I'm saying don't run anything. Whatever the topology, that information that you have, compute the RDF and give it to me in one file. And which file? I'll also define the file name here, rdf underscore initial dot text, which is what you will see in your path, rdf underscore initial dot text. So whatever the output information that you have in that is your initial structures RDF. And we'll also rdf underscore last half dot text is the output that you get after running the simulation. The file name is what you define here. The second time, rdf underscore last half dot text. Is that clear? Okay. Now let's go here. Okay. First thing we need to do is now we are going to exercise. Now LAMMPS has given us some files, right? Like some output. We are like, she asked a question, how do we know it got completed and stuff, right? Let's go over it. Now, first we defined the LAMMPS to create as a system of density 0.85, right? Now let's try to confirm that it has happened. That's the case. Like LAMMPS has created a system of that density. How would you confirm? So if you go, you can just open initial underscore fcc.data, for example. Okay. You see the box dimension in each direction, right? Okay, let me go over what the atom topology file looks like in LAMMPS. First, you define how many atoms are there in the system, 4,000 atoms. And what are the atom types? We just have Lennard-Jones particles, so it's just one atom type. And what are the box dimensions? So 0 is the lowest dimension. So X dimension goes from 0 to 16.75. Y also goes the same way, and Z also goes the same way. So your dimension is 16.75 or something like that, right? And then your masses, we define masses in the input script. Do you remember? So it's one atom type, and that mass is 1. And then we defined atom style full, right? So let's see what it prints out. It prints out the atom ID. So if you have 4,000 atoms, there will be 4,000 rows defining each atom's position, basically. Second column is basically their molecule ID. All molecule is like what, if you have different molecules, there will be different IDs. Here, all we have is Lennard-Jones particles, so the molecule ID is 0. Atom type is 1. So we have all the atoms beats to be the same type, so it's 1. Fourth column is the charge. Lennard-Jones particles do not have a charge, so it's 0. Then the following 3 are XYZ values, coordinates, basically XYZ coordinates, position of those atoms in, like within the box. And the last 3 columns are the periodic boundary conditions, image flags. I'll tell you what image flags are. The image flags could be integer numbers. Let's say image flags are 111. What does that mean? Basically, that means that the atom from the central box has moved outside and is in the next adjacent periodic box, 1. If image flags could even be 10, what does it mean? Let's say image flags are 10, 5, 3 in XYZ, right? When 10, what it means is in the X direction, that specific atom has moved 10 boxes and it's somewhere in the 10 box, right? So in some ways, when you record this, it gives you the information to compute how the atoms are moving within the system. So that is why the image flags are important. So the things that I want you to remember are, again, this could be lay like a 1-hour lecture of what this is. Like, it's an integer number. It tells you at any point in time in which box it is located. Remember, there are periodic boxes, right? Things that you can't see in the simulation. And then if you go scroll down, you will have velocity section. So, but this doesn't have bonds and stuff, so let's not worry about it. So that's basically how the structure of a LAMMPS data file looks like. Yes.
Like the software make sure that if there's something exiting from one side, like say entering from the other.
I'll show you when I visualize it. Yeah.
So I was asking about that.
So when something goes out, it's not that the same particle is entering. That in the next periodic box, that same thing is coming inside. Like, it's the same particle being replicated on all directions, right? So you're simulating an infinite medium in some sense. If particle leaves, its mirror copy will be in the adjacent box, right? That enters. Basically, it's not the same particle. It's not like magic happened.
And
Just like an infinite medium.
And it's just number.
Yes. Yes. So how do I, like, you can compute density by simply doing number of atoms divided by the box volume, 16.75 cube, right? If you do that, you should get 0.85, basically. If you want to check it from the stuff that I'm not sure where. Okay, I think I closed it, the dashboard. So if you go to the output, if you go to that out file that I was talking about, we also print the density in the thermo. You remember thermo command? So you see that density is 0.85 here basically. So it confirms that your density is at what you requested the LAMMPS software to do. And then you have potential energy, and you will see in the potential energy column, the potential energy keeps decreasing, right? It is trying to find the minimum there. Of course, we are running very short steps. If you let it run, it will go even more or it will stabilize. But that's basically the point of it, right? Now that you know the density, let's try to visualize the trash.lj.dump, right? Like through VMD. Now, the way you do it is go to your dashboard and in the click on interactive maps, interactive apps. Do you see an option for VMD down? Click on that. It'll ask some, just make sure the number of hours is 3, everything else just keep it as such and just launch and wait for it to start. Are you able to do it?
Yes, there was one part where, I think you had changed, like I got the errors that said requested reservation is invalid. I missed the instruction. That was.
Just remove that line. Okay, open your job.sh file.
Yep, job.
Do you see something called reservation equal to training?
Yes.
Instead of training, change it to LAMMPS, LAMMPS, all small letters,
Okay.
and then save it.
Also. And then rerun the,
Submit it, yeah.
Okay.
Should run. Has it started for you all? For me, it hasn't. If you see launch option at the bottom, you can just launch it. Yeah, I have to do it again. Again, Grace is a bit slow today, so. Okay, while it's loading, let's just try to look at the output files from RDF that we got, right? So that we don't waste time on it. Okay, what does the RDF file contain, right? Let's look at it. So it has a bunch of comment lines on the start, and you have basically the first line after the comment line, it says, okay, there are 200 bits. Can you see that? Like you just have to open the RDF file. You have to run the simulation to see it, but I would like suggest that you follow what the RDF file is so you know what the columns mean. So the first line that you can see here, it says 200 bins that we defined in this run. And then there are 4 columns. First column is simply the bin number. So you will see that it goes from 1 to 200 if you scroll down, right? Each bin. Second column is basically the R value, right? At this distance, this is the probability. That's what it's saying. So it's R, the second column. Third column is your probability, your normalized probability. And you see that at very short distances, 0. Nothing is such very short distances together. And at some point, you will see some big number appearing here. 64, things like that. So third column is your probability. Fourth column is your coordination number, how many neighbor atoms you have within that bin, but fourth column is irrelevant right now. The columns of interest for us are second column, which is R, and the third column, which is probability. So you will plot probability on y-axis and R as on the x-axis, basically. Okay. So there are two files, but both the files have the same thing. It's just one is for the initial structure and the other one is for after we finish running the simulation. Okay. Let's see if VMD has loaded. Still not.
You have to do it.
It did for you?
Yeah, not people, for yours, you have to redo it.
Oh, did I not do it? Oh, I didn't do it.
I don't know,
It's been crashing, you know. So there's.
Okay.
Did it,
Okay. Cool. Okay, before that, I mean, you all know how to take a text file and plot, right, on Excel sheet or some software. So that doesn't need like any specific dedicated time. But if you take that RDF file and plot the second and third column on X and Y axis, right, this is what you would get. Okay, our initial, let me go, let's discuss this a little bit. So your initial configuration is what the LAMMPS created. Remember, we asked it to create a face-centered cubic lattice. It's a crystal lattice, right? It's arranged specifically in a specific way. And we computed the RDF for it. It looks like this, where there are peaks at specific distances, right? Now, after the simulation finished, after we average, this is the final configuration that you have. The first immediate thing that you notice is it's not ordered anymore. Things have moved around, right? That is what I want to show in the VMD, but that's what has happened. And when I compute for such a configuration, you get an RDF like this, right? And all you see is at short distances, there is some favorable interaction. Whenever you see RDF going above 1, it means there's favorable interaction. How much above 1 indicates how strong the interactions are, basically, right? So this is the first shell at the like within a certain distance there is, and then it goes down, and then there is another peak at a certain distance. There is some favorable interaction, and then decay and go to 1 at long distances. Now, LAMMPS by default computes only until your cutoff, which is 2.5. You can also write a separate code to compute until longer distances as well if you want to see a value going to 1, right? But the question that I have for you is, if you look at this RDF first one and the second down at the bottom, the first one, does it look like a crystal or a liquid? And same question for the second RDF. What do you think first one is? It's a crystal or liquid? It's a crystal. It's ordered, right? You see the initial structure, right? So so this is the typical RDF for any crystals, because atoms are at defined distances. They don't move. So that's why you see peaks at specific distances, right? But as soon as the atoms are jumbled, they become liquid-like. And this is the characteristic RDF for a liquid that you would get. So the second system corresponds to a liquid. The first one corresponds to a crystal, right? Let's see if I got lucky. Okay, good. So let's visualize that two static snapshot that I was showing quickly. So you should see the VMD loading up for you. Okay, so you will have this tab. Do you see that? Okay, so you see file, new molecule, and then you browse. File, new molecule, and browse. And you will immediately be taken to your Scratch folder. Look for MD LAMMPS. Go inside LJ, and you will see trash.lj.dump. Once you're at this step, let me know. Good. Okay. All that you have to do is just press OK, and then you have to tell LAMMPS. This VMD doesn't recognize this, so you have to tell what trajectory it is. So if you scroll down, you will see an option called LAMMPS trajectory. Here. I didn't select. I think my system. Okay, good. Then once you select LAMMPS trajectory, just load it. It's too slow. Okay. Is it good so far? Do you see something appearing? On your screen, I'm asking.
VMD is not good.
That's awesome.
Okay. I mean, if you're interested, I can show you after that how to visualize and like have fun with this. There are many things, but for now, I've just visualized what I'm doing. So under graphics, we'll go to representation. I'll just select VDW. Hope it works for me. It's punishing today. So huh?
Only we can.
Hmm? Oh yeah, yeah. We'll take a 5 minutes break. Let's see. After that, we'll continue. So the first lab will be intensive because we are trying to define everything. From next one onwards, it will be more quicker. We'll just go through it. Okay. Yeah, let's take a 5 minutes break and then we'll restart again. Oh, it did finally for me.
Oh.
So it starts like that and just runs the simulation. It doesn't look as good as what I show on the slide because you change the colors and stuff like that. But idea is for it to just simulate and see how it even load. Yeah, but if you guys want to learn about VMD, just email us and I can go over with you on Zoom, show you what all different things that you could do with VMD, how to visualize things and stuff, so that it looks as good as what you see on this slide, like colorful. Like you can do a lot of things. It's just like any other like software, like Photoshop or something. You just play with colors and stuff to make it look good. And I restart. I start. You got all good? Can start. Okay. So we saw Lennard-Jones system, right? Like basic of how to do. So if you have beats, right? What if you connect those beats, right? Like make it a polymer, like or protein, like where the residues are connected with each other, right? So basically, what we'll do in this exercise is we'll introduce bonded interactions, not just the Lennard-Jones interactions. We also introduce bonded interactions where two things are connected, like beats are connected to each other. And specifically, we will model a polymer 20 LJ beads connected together to form a polymer chain in this case. So we'll model polymer chains of length 20. When I say length 20, it's just 20 beads in a chain. Okay. So let's try to inspect the files first. So let's go to in MD-LAMMPS, you'll have LJ underscore polymer folder. Click on that. You will see three files. Job.sh is the same job submission script. It is going to be the same for all the labs so far and so forth. We're just going to change the input file name, right? So that's fixed. For example, if I show here, it will just be lj underscore polymer.in for this lab for the input file. Everything else stays the same. Of course, the job name I have changed it to lj underscore polymer, but that's a user's choice. And then we have an input script describing the simulation conditions, but we don't have a topology file, right? Like the last time we asked LAMMPS to create as a face-centered cubic lattice to start the simulation. So that is one way. Another way is if it's a simple enough system, you write a Python script to define a data file. You know what should be there in the data file, right? It's easy to write a Python. Everyone knows Python or any little bit? Okay, cool. Okay. I mean, there are these AIs now. So as long as you define it, you can easily define it. But this is a very simple enough code actually. It's nothing very non-trivial or anything. It's just I'm saying, okay, get me 50 chains. Each chain should have 20 beats. Like they're connected by bond. And we're going to define a bond length of 1. Still remember, we are still in LJ units. There is no like any units attached to it. And then I want the data file to be in this data file printed out eventually. And you have to go over it. Basically, all I'm going to do is I'm going to define an atom, define the next atom, connect to the bond, next atom, connect to the bond, and so on and so forth to create a system, right? Because I'm not going to go over the Python script, but that's basically what it does. Okay. Now, you want to run this to create a topology file. So let's go to the terminal. If you are on that path already, it's going to take time for me. Run the Python. You know how to run a Python, right? Like Python, Python, Python space that file name, .py file name. Just run it and tell me what you find. You should also see it on the slides how to run it. It's Python, the .py file name. That's how you run it. Any success? Or you're unlucky as me not to get to terminal. Still loading for you also?
Okay, right now. I got batch job submission failed, reservation.
No, you're not submitting any job. Just run the Python. Don't run dispatch command. Look, like your slide. Python change20.py. Just run that for now. Tell me what you find. CD, yeah. CD, direct folder name, yeah. Correct. That's what you should see. Yeah. I wish I can get a.
I launched it through the. I had my thing open to LG, and then I launched it.
Okay, I got it. Okay. So all you do it is like Python change 20. You should see that Python not found. So basically, you have to load the Python, right? Like, so how do you load Python? Like, for the command to do that is first you need to check what versions are available, if it's available. So you just do module spider Python. So it'll list this BioPython. You can scroll down. It just lists what all is available basically on the cluster. Oh yeah, I could have done that. Yeah. Okay, I got it here. So you see, these are the versions that are available, right? Like, so we just need to load it, one of the versions. So let's just click the last one. So all that you have to do is double click. It will automatically copy on the terminal Python 3.13.1. If you want to exit, it's just Q, press click Q, it will go back. Now we want to load it. So how do you load it? Python, sorry, not Python, module load. Instead of spider, SPIDER, you will say load, and will load that specific version. When you click on it, it will say, okay, there is still some dependencies that you need to load. It's not directly, you can load it. So what you did again, you have to do module spider, but you will check what do I need to load this version successfully, right? So it says module. When I do that version, it says, okay, you will need to load all modules on any or one of the lines below before the Python 3.13.1. So basically I need to load this GCC thing, okay? So all I have to do is again, copy this, press Q, will get out. So it's module, load that first, and then your Python version. Next. If you do this and press enter, that would have loaded. Are you able to load Python? You can see the line that I did, so you can just type that. You're able to do it?
think I already got it.
No, I'm asking him.
Oh, yeah, I'm checking. I had done like a previously module spider Python, but it didn't show me some version. It shows me like a bunch of other bio Python, some.
Yeah, you have to scroll down. Just press downward button. See what you can, it stays sensitive. Just do capital.
Oh, capital Python?
That, type that.
We'll just do more.
Oh, sorry. Right.
I did the same thing too. Good so far. After loading, you have to just run that Python file. It will create you the data file. So it says wrote the change 20.data, expected 950 bonds. So you can compute like where 950 bonds coming from, right? Like you have 1,000 atoms. Each chain has 20 beads. So if a chain has 20 beads, there will be 19 bonds connecting those 20 beads, right? So it's 50 times 19. That gives you 950. So once you see this output, let me know so we can proceed. Good. Are you able to do it? Error?
Yeah,
What error?
I'm just getting, I guess they can't load it. Load has detected all their, all modules are. which is-
You did module load GCC. How would that be? GCC cursor dot table. Your GCC slash dot. 3.30.1. Okay, good.
Thank you.
Then you have to just run the Python.
Okay.
So in the job.sh, just change the reservation name to LAMMPS, LAMMPS, and save it, and then run the job. So while we discuss the files, the job will keep running. So open your job.sh, change it to preservation lamps, and submit it. Sbatch job.sh. Are you able to submit?
It's saying,
It's running, huh?
saying that
Okay, did you type lamps LA here as such? Can you check?
it's failed.
Just remove that line and submit it. It should be fine. Like we did in the previous lab, either just remove it completely and submit. Okay, let's try to look at this input script. While what is there and try to understand how is it different from the previous exercise that we are doing. So you will see a lot of things that are common here. So units LJ, atom style full, boundary, periodic boundary conditions. You want to read the chains 20.data that you just got from the Python script. Mass is 1, pair style is the same, LJ cut, pair coefficients. So here we are defining what the epsilon and sigma here. So you're saying atom types 1 and 1. So two atom types. Here there's 1 and 1. They should have interact with a epsilon of 1, sigma of 1, and the cutoff is 2.5. Now, if you have multiple atom types in the same system, you can define for each pair 1, 2, how they should interact, 1, 3, how they should interact, 1, 4. Like that, you can define different epsilon and sigma and epsilon for each of those. But here we have only one atom type to deal with. The new stuff that you will find here is the connectivity. So you have connections between the beads. So you need to define bonded interaction. So we will define a harmonic potential, basically. If you want to know what it is, again, as such, you say, like the command, you just go and type bond style lamps. Will take you to that command bond style, and you can read. So basically, it's simulates it with a bond style harmonic. I should have typed bond style harmonic lamps, and you search that. Basically, we will simulate it with this potential. This is the harmonic potential where we give a spring constant value K and an equilibrium bond distance, which is R naught, right? So depending on how strong your K value is, the bond will fluctuate close to that R naught value. Basically, that's what it does. That's the harmonic potential. So here bond coefficients, we are saying K is 100. That's a spring constant, right? And then I want the R naught to fluctuate around 1, basically, right? Not too much away or too, less than that. Then there are these exclusions, which is special bonds Feeney. What that does is, if 1 and 2, let's say there are atoms connected to each other, right? If 1 and 2 are already connected, I don't want any LJ interactions between them. I just want bonded interactions between them. So basically that special bonds Feeney basically does that. It excludes them. It excludes those two directly connected atoms, the LJ to be applied on those directly connected atoms. Only the bonded potential applies. The LJ potential only applies to atoms that are not directly bonded to each other. For example, in a chain, first atom and the 20th atom, first atom and the 15th atom. But when something is directly connected and they are like this, I don't want an LJ interaction. They're already connected, right? What am I going to? They're not going to move away and out and stuff like that to see anything, right? So just trying like exclude it for now. And as I said, neighbors, it just builds neighbors to keep updating and computes only within that pocket of like neighbor, the atom potential energies and forces. We are creating velocity, thermostyle. We are printing whatever we want. As I said, it's a custom thing. I'm printing temperature. All that you have to do to know what all lamps can build is just type thermostyle lamps. It will tell you everything that lamps can print, right? And it'll tell you the keyword and you can go and print it. For example, if you have electrostatics and you need Coulomb energy, there is a keyword in lamps. Like I don't remember a top of my head, but you can just give that keyword here. That is why I'm saying there is no point memorizing these commands because there's a good documentation. All you have to do is just go search for it. And I'm saying print every 500 steps. And initially, when we created the system, the density is not at 0.85. So this is another different thing. So previous exercise, LAMMPS itself created a system that is at density 0.85. But here I used a Python script to define an initial structure. It may or it may not be at 0.85. So I need to get it to 0.85. So what I'm doing is I'm defining a target, row target, which is 0.85. I'm defining, this is how you define a variable, like how in any code, any programming language you'll define. In LAMMPS, you define a variable using the command variable, some name equal 0.85. And then I'm also defining another variable called row, which is equal to density. So density is basically an internal LAMMPS keyword that computes the density of that current, whatever that initial structure is. So it keeps a record of it. And I'm saying, okay, I can scale it. I need to scale it to go to row target. So I'm scaling it as v row v. So this is how you access a variable in LAMMPS. It's v underscore the variable name that you give. So it's v row divided by v row target to the power 1/3. So basically you're getting a scaling factor to go from whatever that density right now to the target density. And so these are just Lx, Ly, Lz are all internal variables of length in x, length in y, length in z. X low, xi, y low are lower dimensions of x, and xi, yi, zi are higher dimensions of x, y, z. And what I'm doing is we now have a scaling factor called a to go to that. So I'm saying, okay, now if this is my lowest dimension, I want the higher, you know what lower higher dimension is, right? Let's say your box size is 10 in x. The 10 could be either it could go from 0 to 10 or it go from 5 to 15, it go from 50 to 60. At the end of the day, it's still 10, right? You can define anywhere in space the like lower and higher dimensions. So you're saying lower plus scaling factor times the current VLX. So you're going to scale it so that you go to the target density. So before you deform anything, you're saying print me the row to start with. Okay. And then there are these time steps that are the same as before 0.005. Then like we will run an NVT temperature with a, like some damping factor like at 1. So what that basically means is like how often should I monitor whether it is close to my target temperature or not. So when I run NVT, it is constant number of atoms, volume and temperature. And I'm saying temperature is 1 and 1. How often you want to dampen it so it's close to a temperature of 1. And the variable, so here basically we are trying to deform the box. So this is the new command that you look at, fix deform. So what it tells is, okay, I'm having this box. I want to go to this box, do it for me to get to that density. So that's what fix deform does. And here what we are trying to say is in X dimension, our final box size should be XLO0, which is the lowest dimension, and XHI2, which is the variable defined here where we scale it to go to the target density. Same thing applies in Y and Z and remapping X. So now when you're resizing the box or expanding the box, the atoms could move out and stuff, right? So we are saying LAMMPS, okay, if my box size changes, remap all the particles to put it inside the box. That's what remap does, remap X basically. And run it certain and this many steps. Basically, instead of giving 10,000 directly, I have defined a variable n def equal 10,000 and I'm running it that much time. And then after running, I just want to unfix this deform. All I'm doing, I'm not doing any simulation. I'm trying to run a simulation to get to the target density, right? This is one way to get to the target density using the fix deform command, okay? Now, after this process has happened, after deform, I'm asking it to print the final row. So ideally, if everything went well, our final density should be 0.85. That is what we're getting at, right? Before we start any simulation. So like any programming language, you can also use the print command to print it, right? And then after all this has happened, I'm saying, okay, you have changed the box, you have gone through so much, settle for a bit. So run 2000 steps for system to settle a little bit with whatever that is density that is it has achieved. Then after all that has happened, I'm saving a snapshot at change 20 at density 0.85. So we have an initial topology file that we got from the Python script. After all this has happened, I'm saying, okay, record a new topology file at that correct density that I want. So just in case if I need it later, I will have it. Then we are compute RDF. RDF we have already seen. We have already seen RDF. There's nothing new here. We are just computing RDF between all the atoms. The only difference is atoms are connected to each other in this case. And then we have mean square displacement. This is a new thing. So what it does is mean square displacement, nothing but how much atoms move in space, right? So we are just trying to record how much, like if you ran 10,000 steps, how much atom, a particular atom has moved over time, right? Now, since this is a system of same type of atoms, we will average through all the atoms to get a average distance, how much it has traveled. So the command to do that is compute MST. You're saying all the atoms, compute all the atoms, the MST for me, and then you're using fix average time again here 100 100. Can you tell me what that would mean? Like n every, n repeat, n frequency, right? So what that 100 100 would mean? So it will print MST values at every 100th step, because that's n this last 100 is n frequency, right? At every 100th step, it's going to print me the MST values and then repeat it once. So you're not going back in time. You're printing exactly at the 100th step, right? So this n every kind of doesn't make any sense here, because anyway, you're not repeating it. So whatever number there, you're just going to stop there. And basically you're saying at the 100th step, print me, at 200 step, print me, at 300, at 400, at 500, 600. So you're recording how much it has moved over time. Why do you think it doesn't make any sense to average here? Why you are printing at that specific instant of time? Because when you average it at each time, the movement is different, right? How much it has moved. So it doesn't make any sense to get an average. You're better off seeing at that instant where how much it has moved, at a specific instant, how much it has moved, and so on. And then you're dumping the trajectory like LAMMPS, like using the dump command, and then running it for 20,000 steps. So all the same, right? So you see, there are so many things that are common. Only a few additions. The main addition in this case, I would say, is the introduction of bonded interactions, right? Bonded potential, right? We're just trying to make it a little bit more complicated than the previous lab exercise. Is that clear? Like again, at the end of this course, it might look like you might not have everything in, but when you look at it, at least you get an idea of, okay, this is what he told, like, or I can go to the documentation and look at, but if at any point in time you need help, you can always email us and we can help with that specific particular input script that you're working with. Okay, we are not going to visualize it because I'm not able to. So, but we will do it in like VMD. It's not loading for me. Now, this we also computed RDF for this polymer, right? We also computed RDF for the last exercise LJ system. The only difference between the two is in the second case, the system, the things are bonded to each other, right? Now we have two. If you go to your dashboard, you will see RDF underscore. If I refresh it, hopefully it has run. Okay. You see there is RDF underscore last half dot text. We already discussed what this is, right? We are interested in the second and third column, distance and probability, right? If I take this and plot it alongside the one from the previous, right? You would see something like the left-hand side, okay? What do you think is the difference that you're seeing? So pure LJ is orange line and LJ polymer is the violet one. What do you think is the difference? So the peaks happen at the same distance, right? But the height of the peak is different. Any guesses why that would be? What that the only difference between the two systems is there are bonds between the beads, right? Why is there? So when the height is lower, it means they are not coming closer together. They are not able to come closer together much. Or there is not enough attraction to pack in that first shell. It's simply because the connectivity restricts it from coming together, right? Like there is some restriction for the atoms, right? They can't come to, and also remember, we are also excluding the bonded interactions that are connected to each other. So it makes sense why it is somewhat lower, even though it happens at the same distance profile. Now the MST, I'll show you the file, but this MST curve basically tells on y-axis is there how much it has moved. It's mean squared displacement. It's just a square, right, of the displacement taking a mean. You have pure LJ and you have LJ polymer. Can you instantly tell what is happening here from this? So one is pure LJ MST is higher, much higher than LJ polymer. Remember, we are running only short simulations, right? Ideally, you should run long enough to compute diffusivity and things like that. But we're trying to get a sense of what this means, right? When you look at pure LJ, your MST is much higher compared to a polymer. It makes sense because when things are connected to each other, if one bead has to move, it has to drag all other 19 beads with it. And so on. So the dynamics is somewhat slower in a polymer system. But when it comes to the first system, LJ, it's just individual beats. If it wants to move, it will just move freely. It does not depend on something else, right? So that's why you see the displacement to be a lot over the simulation time here. Now, I go to the dashboard. If I load the MST file that command printed, basically what it prints is first column is the literal time step at which you computed MST. Second column is the actual times. So basically you have time step, right? 0.005 or whatever they define. That multiplied by the first column is the second column. It's literally the time. So first column is time steps. Second column is time in terms of like the steps that you're defining. That is usually called as the LJ time in this case. Third, fourth, fifth columns are displacement only in X direction, displacement only in Y direction, and displacement only in Z direction. The last column is of interest to us, which is the displacement in all three directions averaged out. Okay. So the plot that I just showed on the slide is between column 2, the LJ time, and last column, which is the displacement in all three directions. So that is all I have plotted. I have plotted the last column on y-axis and second column on x-axis. Is everything clear? Think good? Okay. Now we get some sense of like how simple systems work and how introducing bonded interaction. Now let's try to go into all atom, right? Instead of simply defining beads, let's define an actual water molecule, which is H2O. So there are going to be hydrogens and there are going to be oxygens and stuff, right? So building on previous two labs, we will now introduce angle constraints. Now we don't have just bonded interactions. We don't have just like, we not only have Lennard-Jones interaction, we'll now have angles, like water has H2O, right? Like, no, you need to preserve the angle of water molecule for it to be a water molecule. And then there are electrostatics, like oxygen has like partial charges and stuff, right? So you need to treat that. So what we'll do is we'll use something that is commonly used. There is a model called TIP3P model. Okay, it's just a model with some force field parameters. Think of it as some numbers that people have optimized for something to behave like a water, right? And then we will perform constant pressure simulations. The objective here is to get to the water density at room temperature. Any idea what is the water density at room temperature at 25 degrees C? 1 gram per cc, right? Like, or whatever unit you want to say, 1 gram per centimeter cube in this case. So objective is, can we do a simulation where the system reaches that, right? If it reaches that, then we know that, oh, we are actually doing a correct water simulation because it behaves like a water, right? So let's look at the input files. So if you go to, if you go outside, you will have another directory called water. If you click on that, you will see 3 files. Job.sh, by now you know what it is. It is to submit a job. Like, make sure you change the reservation name or completely remove that when you submit it. I would say just go ahead and submit the job for now, like, so that while we discuss the files, it will get done. Are you able to get access to terminal? No.
That you want us to do the job, the ask dash job,
SBatch, yeah, job.sh, just submit it if you have access.
first,
Just remove, you have to change it to LAMMPS or just remove that line. Let it, are you done? Okay, let's go over the input file. Okay, now we'll just try to go over only the differences because most of them will be somewhat will be similar. Units real. Now we will be dealing with real units. We are actually simulating a real water system, right? So you can learn more about what are the different units in LAMMPS. So units real means like you're literally going to simulate an angstrom, like gram percent, like the density you will get in gram per centimeter cube and all this stuff. You will get in real units. That's why it's called units real. Okay. Atom style, same boundary condition, same neighbor command, same special bonds. You're going to in what when you simulate pure water, like you're basically saying like 1, 2, 1, 3 interactions, like don't exclude them. Like all the intramolecular LJ and Coulomb. Basically, what it does is within a water molecule, there are no LJ and Coulomb. That's what it says. There is interactions between water, but not within the atoms, within like the hydrogens and oxygens within the water molecule don't interact. There is a reason for that, but then you're going to read, I'll tell you what the reason is, but you're going to read the data file that is there in that path, water_tip3p.data. Then that data file is for only one water. Now, there are different ways to create a system, right? The data file has only one water molecule. Now, if I don't want to simulate just one, I want to simulate bulk water. So there is this command called replicate. And I'm saying, okay, take that data file and replicate 10, 10, 10 times in all directions. So that gives me 10,000 water molecules. 1,000 water molecules, basically. And then after replicating, I'm saying, okay, after you did, write me the data file, right? So the data file will have 1,000 water molecules. So it will be 1,000 times 3. So it will be 3,000 atoms because each water molecule has 3 atoms. Then in the tip3p model, hydrogen has mass of 1.008, oxygen is around 16, like that's standard values, gram per mole. And then there are charges for it, like 0.834, 0.417. And then there are water, oxygen, hydrogen are bonded, right? So you are going to treat it as harmonic potential, and the K values and like this stuff are given. But in water molecule, the bond and angle are not really, you don't need to apply a potential in the sense, that's why you see the K value is 0. There is no spring constant. The reason is we are going to simulate water molecule as rigid. Like we are going to keep every molecule preserve its angle and bond throughout the simulation without it changing. Because remember, in simulations for water to behave as a water, it has to be at a certain specific angle and the bond length has to be a certain bond length. We don't want to disturb it. The reason why people came up with this idea of just keeping it rigid is because water is a very common solvent that you will find in a lot of simulations, whether it is like you want to simulate proteins or you want to simulate some materials, water is always a common solvent. So you want water to behave like a water, right? So what we instead do is, let me go down a little bit. We use this command called fix shake. What it does is, as the comment, you see a comment line on top, it says, I'm constraining the OH bonds and HOH angle to be the same throughout the simulation, basically, right? I don't want to disturb it. And then pair style, previously we had just LJ cut. Now we have electrostatic interactions, Coulombic interactions. So COUL_long. Now, the reason COUL_long you see is electrostatic interactions are long range, right? So they don't decay that fast, like they decay very, very slowly. So you have to compute it long enough. And then we are saying a cutoff of 12 in the real. I'll quickly show you one thing. When you type units real LAMMPS, it will tell you what it actually is. So if you go down, you will see in units real, mass is in grams per mole, distance is in angstrom, time is in femtosecond, energy is in kcal per mole. So there are some real units that you could attribute it to. So the outputs that you get in that simulation will have those units. So you can directly compare it with what you get from experiments in this case, right? So in this case, when I say 12, it is 12 angstrom. That's the cutoff, right? How did I come up with that number? So usual ballpark is in LJ, we use 2.5, right, as a unitless cutoff. It's 2.5 times the heaviest atoms sigma. In water, the heaviest atom is oxygen, right? Heaviest, I think oxygen as about, let's see, its sigma is 3.188, right? So about like 3 times or 4 times that sigma is usually taken as the cutoff. That's the ballpark. So 4 times of 3 is 12, right? So we just define that as a cutoff. And then assigning velocities and then printing the trajectories, dump command, it's the same thing. And then you have to fill a line here to compute something, but I'll come back to it. We are last in the previous simulation, we did NVT. We didn't change the box size through the integrator. Here we are doing something called NPT. So to get the water to go to its direct desired density, you need to apply some pressure, right? In addition to the temperature. So what in NPT you do is temp 298, 29800. So you're going to run it at 298 Kelvin. And then there is command called ISO. ISO means pressure in all three directions, same pressure. You could also apply different pressure in different directions, but let's not go there. ISO is like same pressure in all directions, and 1 it means 1 atmosphere. Right? So you see, it's directly related to what you could do in experiments, for example. So I'm applying 1 atmospheric pressure on all three directions and running it for 35,000 steps. And we want to see whether the water gets to its desired density or not. Experimentally, we all know water density is 1 gram per cc at 298 Kelvin. We want to see what it is. Now, to check, we need to compute the average density at the end of the run. Now we have an exercise. Type the command here to compute water's average density from the last 5,000 steps of the run. So you run it for 35,000 steps, right? I want to only average over last 5,000 steps. What command would you use? We are averaging so far in the previous labs, right? Like what command? The average time command, fix average time, you remember? N every, N repeat, N frequency, you remember that thing that we're discussing? Right, that's the line that we need, basically. You have the output in the slides. If you want, you can copy and put it, or if you want to try it yourself, type it and like test yourself, you can do it, or take it from the previous lab exercise, but try to fill that line. So you will have the output here, here basically. So this is the line we need. And you go here. This is the line. Can you see that it is doing what we want it to do? It is only averaging over last 5,000 steps. The numbers that make it like happen is that N every, N repeat, and frequency numbers. So we are running the simulation for a total time like 35,000 time steps. I'm asking the command to print me the average density only at 35,000 time steps at the end of the run. And at 35,000, I'm saying N repeat is 5,000. So I have to go back 5,000 times backward in time. And what is the interval? 1. So basically, I'm going to go every time step 5,000 times before 35,000. So the average is going to happen between 30,000 steps and 35,000 steps. So you're averaging the last 5,000 steps to compute the average density. Why am I not computing right from the beginning? Because it could be at very different density, right? If you assume those as equilibration period, if you include that in average, that will obscure the value that you're seeing, right? So you would rather wait for a bit, let it equilibrate, and only look at the last bit. Now these are very short. You should ideally have run longer, like. But I figured out by testing and trial, like we get there, like 35,000 steps. So I was like, okay, last 5,000 is good enough. After you add, now before you submit it, if you let's see, I think I saved it, hopefully. before you ran it, if you open the output file, you would see some error because that line was not filled. Right? Now, if you run it again, it will, you have to just do sbatch job.sh, it will run, simulation will run, and we'll look at the average density after that. And now the portal itself is not loading. Okay, now it's loading. Yeah, I have to change. I don't have delete, but I can change it to LAMMPS lamps. Save it.
Oh. Yeah, I'm getting that,
What?
exactly what you just thought.
But are you changing it in your job slip? I got the reservation name wrong. So open your job slip. So that line you don't have. Why I want to use something again? You should know. No, but go to the input file. Water. Now you should submit what error are you getting? Oh, no, it's not.
Where you go? The count.
Yeah, that is fine. It's getting submitted, right?
Oh, then yeah.
Yeah, that's what you need to get. I'm saying this is, I got this error.
Oh, I deleted the tree.
Yeah.
Okay. Oh, right.
Is it running for you all? So you should go to your output file. You will see that the steps are being printed out every 500 steps. Did you copy it correctly from the slide and put it exactly? No, we got it. File. On the slide it was otherwise it recognizes it as a separate command or something and it doesn't know what it is. So you have to go to your out file and you will see at the bottom it will. Okay, let's look at actually the V row column density. Do you see at the starting, when you started the simulation, density was 2.49 G per cc, very high, right? What happens is immediately it relaxes. As you can see, if you see through the time, you see that it'll go towards 1, 0.99. That's what happens, please. We're almost there, 30,000 steps. So once the simulation is done, you will see the file average_density.txt that will have the average value. Just as a confirmation for us what densities water systems are. Okay. For me, it's done. So I'm just going to open it. And you see that at 35,000 steps, you see a density of 0.995 gram per cc, right? So you see that the water, you can run it however long you want. The density will always fluctuate around that value, right? Because we are actually simulating a real water in this case. And now you can compute any properties that you want with water. You can compute RDF. A good exercise for you all would be, you know how to like have the RDF commands and MSD mean square displacement command from previous lab. Try to take those, add it here. Of course, you will get some error or something. Go look at the documentation, see what needs to change. And if you can successfully compute the radial distribution function and mean square displacement for this system, they're almost there. Like, you know, all that you need is, okay, if I have the documentation, I can go read and change commands and like, you know, play. Yeah, if the VMD was like fast enough, I could have showed the visualization. Just this is how the box of water would have looked like, the one that you're simulating with all the water molecules around. So we started with a simple bead system. We add in this next exercise, we added bonds. The third exercise is on top of all those, we added angles, electrostatics, right? I don't think we'll have time. The last exercise is polymer in water. So we are trying to make it more and more complicated, right? Now what this is it's a two-component system suddenly. You don't have just water. You don't have just like LJBs. You have two components. You have a polymer chain put in a water, all right? So specifically, we like the idea I had was to show how to simulate 5 polyethylene glycol chains, which is like as like used across like medical, industrial, commercial sectors. So that's the chemical formula basically. I wanted to show how 20 repeat units would do using Cham-Gui polymer builder. Can I? Is it okay if I show you guys like? Guys, good. Like I can show you how to prepare the system at least the polymer builder. Okay. So we're just going to see how to prepare the system, right? Because you can prepare the system with a Python script. In one exercise we saw, you can prepare system by using LAMMPS commands like the first exercise. In the third water system, you can also replicate the water molecules, right? But it becomes more and more complicated. People have written like things like Cham-Gui that you saw in the morning, how to use it to create a polymer. It's very easy. There's so simple. Go to Cham-Gui that you went in the morning. If you want to do it, you can do it with me together. But you click on input generator, you have to log in, of course, with your credentials. So once you're inside, on left-hand side, you will see a lot of options. One option that you will see is the polymer builder. Your polymer builder, you have to just click on that. Are you on this page? So you can prepare 3 types of systems. You can prepare just a single polymer chain, or you could prepare a solution. Solution is a polymer chain in some solvent. Could be water, it could be some other organic solvents or whatnot, right? Or the third one is a melt. Melt is nothing but just polymer chains. Just a box full of polymer chains, like second lab that we did. We had LJ polymers. It's just that we are dealing with a real polymer in this case, which is polyethylene glycol. Right? You can simulate any polymer that you want. The good feature, like if you try to do solution, so the good thing is there are many polymers that you want to build here. So in the select unit option, if you click, you will see options like amines, amides, esters, and so on. In oxides, you will see an option called polyethylene oxide, or okay, I actually meant to say it's polyethylene oxide, not glycol. But polyethylene oxide, right? Let's say you want to create that system, polyethylene oxide. Click on that. PO, it says that chemical structure that you have, and you have to cap it on both N and C terminals. So on one side, it's going to be OH. In the other direction, it's going to be OH, like to cap it on either. And if you want to, how many times you want to repeat that monomer that is inside, right? Within the bracket. It could be 20, it could be 100, it could be 1000, right? Depending on how the molecular weight that you want to simulate, right? So once you define that, you just click next, and okay, it's still loading. Is it fast for you guys?
It just finished.
Everything is slow today. Okay. So I mean, I don't want to simulate such a big box, so I'm just going to say 50 angstrom. And how many chains I want, I'm just going to say 5 chains. And the good thing about this feature is in solvent, you will have so many options if you want to simulate other than water, acetone, octanol, propanol, whatnot, right? So, but here, just to keep it simple, since we already worked with water, we'll just keep water, and you can choose how many chains you want. Just going to go with 5 chains. So three, then box size, I'm going to define 50 angstrom, and I'm going to say generate systems. So like how James was showing in the morning, if the charm does it, just prepares using charm, like, files. It runs somewhat faster than the protein system in the morning, not that slow, typically. Depends on how long the polymer that you want to simulate. Yes. Is it okay if I take 3 minutes to finish, or should just cut it off? Huh? Say it again.
Yes, sure.
Well, let's do this. So you have all the screenshots here, right, on the slides. Basically, what is going to happen next? You can try to create the system. It'll, at the end, all that it will give you is this tar file that you can, like PGZ file that you can download, unzip it, and it will have all the input files, submission scripts. Like submission script you won't have, you can copy from the previous exercise, put it, and just run it and see what happens, right? Maybe this could be a good exercise. But if you want to work more on this and like stuff, like just email me, we can have like schedule a meeting time. I can go over it as well, right? But the idea is for you to have some general understanding of what LAMMPS can do a lot of other things complicated than what we just discussed. But that's pretty much it. And with that, this is how that system would have looked if we had visualized in VMD. If you also want help with VMD, like we can like email us, we'll be able to help. So this is there is a slide page like where it says like the links and documentation to get help. And then finally, there is a link to give us feedback. So you can go to that link. We will really appreciate if you can give some feedback, what we can improve, or what topics you might be interested in that could be added to this to know more. So we could come up with or improve this course much better next time.